When we talk about how ions form from elements, the periodic table isn't just a list of elements, it's actually a map of behaviour. And once we understand how to read it, we can predict whether an element will form an ion, what charge the ion will have, and whether it's likely to lose or gain electrons. So let's start there. If we look at the periodic table, there is a very distinctive line. It's a zigzag line, sometimes called a staircase. It runs just below boron, above aluminium, and then follows a perfect staircase going down. This line is important because it separates all the metals on the left of the periodic table to the non-metals on the right of the periodic table. And the metals on the left, they tend to lose electrons. So overall, they will have more protons. They become a cation, which is positive. The non-metals on the right, they will gain electrons. Overall, they have more electrons than protons. So they become anions and they are negative. A useful way to remember this is a little cringe saying that we have in the science education world, and that is cats, meaning the cations, are positive, as in cats purr. So we say cats are positive. Like I said, it's a little bit cringe, but it's so useful. If you always remember that, you'll always remember that cations are the positive ones. There is one important anomaly, and that's hydrogen. Hydrogen is a non-metal, but it commonly forms a positive ion, H+ ions, by losing its only one electron, and it makes it very unusual and very important, especially in acid-base chemistry. We use group number to predict ionic charge, and one of the most powerful ideas here that the element's group number tells us how many electrons it has in its outer shell, and that immediately tells us what ion it will form. So group 1 will form a 1+ ion, group 2, 2+ ion. And when we come over here, it's a little bit different because they form negative ions, but the group number still gives us an indication of what the charge will be. Let's fill in a blank periodic table of ion trends, and that way we will look at the important ions we need to know in ionic chemistry. Here's our blank periodic table. Let's name the groups. So we have group 1, group 2. We're not going to worry about the middle here. That's the transition elements. Now over here, this is group 3, 4, 5, 6, 7, and 8. The modern numbering is in the teens. If you look at this periodic table, you'll notice that's 13, 14, 15. I'll zoom in for you. Notice 13, 14, 15 and on, but in bracket the old numbering's up here, and that's what I think we're focused on. This is old numbering. Actually, you'll notice this is even called group 0, but we won't worry too much about that. Back to our blank periodic table, and let's fill in the groups. So the first ion in group 1 is hydrogen, and hydrogen makes a positive ion, so H+. Then we have lithium, sodium, potassium, rubidium, and cesium. With group 1, the reactivity increases as we go down the group. That is because the outer electron is further away from the nucleus and it's less strongly attracted. Cesium is therefore the most reactive of group 1 metals. Group 2, that's the alkaline earth metals. Group 2 contains, let's take a look, beryllium, magnesium, calcium, strontium, and barium. Now, although beryllium sits in group 2, you would expect it to form a simple 2+ ion, but it is so small and highly charged that it behaves more like a covalent element than a typical metal, which is why we almost never use it in chemistry. So we will start with magnesium, and these will make 2+ ions. Then we have calcium, strontium, and barium, the 2+ on. And like group 1, their reactivity increases as we go down the group. Barium is particularly important at advanced level because many barium compounds are insoluble, making them useful in precipitation tests, especially for sulfate ions. Now let's move over to the right side of the periodic table, and we'll start with group 7. This is the halogens. Group 7 includes fluorine, chlorine, bromine, and iodine, and their reactivity increases as we go up the group. That is because they are going to attract electrons. So each have 7 electrons in their outer shell. They need one more, and the attraction comes from the protons in the nucleus. So this is the atomic number 9 for fluorine. Fluorine has 9 protons, so fluorine will attract that 1 electron to achieve a full outer shell. As we go down the group, the positive nucleus is further away from the outer electron shell, and so the attraction decreases as we go down the group. Being in group 7, that means they all need to attract 1 electron, so overall they form 1 minus ions. So we have fluoride, chloride, bromide and iodide. If you notice, I didn't say fluorine, chlorine, bromine, iodine. That is because once they become ions, they're no longer halogens, they're actually halides. Their names end in IDE. So fluorine became fluoride, chlorine, chloride, bromine, bromide, and iodine, iodide. Next, we'll look at group 6, and the key elements here are oxygen and sulfur. So oxygen, sulfur, again, we won't worry about these ones down here. They're not used in advanced chemistry. And as they're in group 6, they need to gain 2 electrons to have full outer shells. And so they make 2 minus ions. And they become oxide and sulfide. Group 5, the nitrogen group, they need to gain 3 electrons, forming 3 minus ions. And we deal with nitride and phosphide here. So nitrogen becomes nitride, which is a 3 minus ion, and phosphorus becomes phosphide, again a 3 minus ion. Next, we will discuss the noble gases, which is this group here. Group 8 could be called group 0, and they are helium, neon, argon, krypton and xenon. They don't form ions because they already have a full outer shell, but their importance lies elsewhere. When elements form ions, their goal is to achieve the electron configuration of the nearest noble gas. For example, oxygen, group 6, gains 2 electrons and has the electron configuration, therefore, of neon. And this drive for outer shell completion explains almost all simple ion formation. So we will make a note of these elements on our table. And I've done that in black so we don't get confused with the actual ions that we need to learn. Next, let's take a look at carbon, silicon and boron. So elements like carbon, boron and silicon, they sit very close to our zigzag line. And for them, either losing electrons or gaining electrons would require far too much energy, and it's much easier for them to form covalent compounds by sharing electrons. So you won't see boron, carbon or silicon ions. However, aluminium is the exception. Although it's in group 3, aluminium commonly forms a stable 3+ ion, and it appears frequently in compounds and is an exception you'd expect to recognise at this level. Finally, let's take a look at the transition metals. That's this group here. There they are: scandium, chromium, manganese, that's a common one, iron, copper of course, and zinc. Then we have silver down here and gold. Now the transition metal electron structure does not follow an octet rule, which allows them to form ions with multiple oxidation states. Some key examples we need to know is zinc. We need to know that zinc forms a consistent 2+ ion, and silver forms a consistent 1+ ion. Now others vary. Copper, we have copper 1, that's a 1+ ion, and we have copper 2, that's a 2+ ion. And you notice the brackets here with the Roman numerals, and that is because, like I said about oxidation states, so due to oxidation states and indicated by Roman numerals, transition metals form several stable ions. These are the 2 ones I think it's worth us knowing. Maybe we can make a note of those. We've got Cu+, Cu, 2+, and then we'll do iron, 2+ and 3+. And there we are. And like I said, chromium, manganese and other transition metals, they form several oxidation states, but it's far too much to remember. As you come across them studying, you will get to know the relevant ones, but quite often these will be given to you in an exam. So that should cover really everything you need to know about periodic table, ion trends, all the relevant ions. And by understanding how ions form from elements of the periodic table, it stops being something we memorize. It actually becomes something that we use. And once ion formation is completely secure, everything else, naming compounds, writing formulae, balancing equations, becomes far more logical. This was Sally from Learn Page by Page. Thank you so much for watching. I'll see you next time.